Now we extend our discussion on heat equation to problems where the ends of the rod are insulated. In this case, heat is not allowed to escape from either end. So the ends of the rod are insulated at both ends. So this means that the heat is not allowed to escape from this end. So the boundary conditions for this case becomes like this. So when x is equals to 0, the boundary condition becomes del u over del x equals to 0, and when x is equals to L, the boundary condition, which is del u over del x, becomes 0. So we can simplify this where the PDE of the heated rod is the same as before, where del u over del t equals to k square del square u over del x square, where k square is constant with the boundary condition is the first order of partial derivative, which is equals to 0 when x is equals to 0 and x equals to L. And the initial condition is when t is equals to 0, the value u is equals to function of x, where for this case, the solution of the PDE becomes like this, where uxt is equals to half d naught plus the summation of dn cos n pi x over L times with the exponential to the power of negative n square pi square k square t over L square, where d naught and dn are the Fourier cosine series given by this equation. Now let us try this example from quiz 7b3a. Use the method of separation of variables to solve the initial boundary value problems. Given the PDE is ut equals to uxx, where here we know that k square is equals to 1. Okay, and the length of x is equals to 1. And then this is the case of boundary condition, where the boundary condition is the first order PDE, where when x is equals to 0, the boundary condition equals to 0. Same goes when x equals to 1. And the last one is the initial condition when t is equals to 0. So for initial condition, it is equals to fx, where fx is equals to 2 minus 3x. Now we have identified all the important parameters needed in order to solve this. So from here, using the formula that we have discussed from the previous video, from the previous slide, then we can get the coefficient of d naught and dn, where d naught is equals to 2 over L 0 up to L fx dx, where this is equals to 2 over 1, which is 2, 0 to 1, fx is 2 minus 3x dx. Then we can solve this integration. We get 2x minus 3x squared over 2, 1, 0, and we will have 2 times with 2 minus 3 over 2, which is equals to 1. So this is the value of d naught. Now we proceed to finding dn, where dn is 2 over L times with the integration from 0 up to L fx times with cos n pi x over L dx. So solving using tabular method, then we take the second differentiation, where here this will get -3, and integrate cos with respect to x, we get sine n pi x. Then we differentiate the inside of sine, we get n pi, and the last one is 0 negative cos n pi x over n squared pi squared. So now we substitute all this into the n, where we get 2 times with 2 minus 3x over n pi times with sine n pi x minus 3, this will be minus 3 over n squared pi squared cos n pi x, where the limit is from 0 up to 1. So substitute into the equation, we get 2 times with -1 over n pi sine n pi minus 3 over n squared pi squared cos n pi minus with 2 minus 0 sine 0, which will be 0, and the last one, this will be cos 0, which is 1, so plus 3 over n squared pi squared. Then we simplify this, where sine n pi is equals to 0, and this can be represented as -1 to the power of n. So we expand this 2 times with 3, we get 6 over n squared pi squared times with 1, and this will be minus -1 to the power of n, or we can write it as when n is equals to 1, we get -1, 2 times 6 will be 12 over n squared pi squared, where n is equals to odd number, and when n is even number, it will be equals to 0. Then we can substitute the coefficients of Fourier cosine series into uxt, where uxt is equals to 1 over 2 times d naught, where d naught is equals to 1, plus the summation of dn times with cos n pi x times with exponential minus n squared pi squared, k squared is equals to 1, so times with t divided by l squared, where l is equals to 1. So this become like this. Now we expand this summation. We get when n is equals to 1, we have this. And when n is equals to 2, plus when n is equals to 3, and the last one when n is equals to 4. So substitute d1, d2, d3 with from the n. We know that when d2 or even number, it is equals to 0. So this will becomes 1 over 2 plus 12 over 1 square pi square plus 0, and when n is equals to 3, we will have 12 over 3 square pi square times with exponential and so on. So now we can simplify the solution. We can take out 12 over pi square and write the summation starts from 1 to infinity, 1 over, and you notice here this add with 2, or we can say that this is the odd number. So this will be 2n minus 1 times with cos, same goes with this part. So this will be 2n minus 1 pi x times with exponential, and same goes with this part. So for negative, we just remain negative 2n minus 1 square pi square t. So this is the solution of the PDE with given boundary condition and initial condition.